All right, today's lesson is on Newton's third law. You've already learned Newton's first law, which is the law of inertia. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion, or better, the resistance to an object's change in motion. So the more massive an object is, the more unlikely it is to change its state of motion. And the less massive an object is, the easier it is to get it into motion or to change its state of motion. Remember, it requires external unbalanced forces to change that state of motion. And that's where Newton's second law came in, which is F equals ma, or the net force equals mass times acceleration. So if you know the net force, you can figure out the acceleration of the object. Newton's third law is another very, very important law to understand, and we're going to learn about it now. Some of you may already know it as the action-reaction forces from your magic school bus days or wherever it may be. You've probably heard of, for every action, there's an equal and opposite reaction. And that, is a fundamental physical law of the universe. And it is, in fact, Newton's third law, and that's what we're going to see now. Okay, so guess the forces. Well, what we've got here is a cat that's being strung up by two ropes. In this case, they are force sensors. They calculate the amount of newtons of pull acting on the cat. So one is pulling this way and one is pulling that way, and they're attached to a pulley that has a mass attached to the bottom. The mass at the bottom is 1 kilogram. Now, just for simplicity's sake, let's say that is 10 newtons of force. So 1 kilogram times 10 meters per second. We really know it's 9.81, but on Earth, and we'll say it's 10. So we know there's 10 newtons of force pulling down on the string. What is the force pulling on this arm of the cat, and what is the force pulling on that arm of the cat? So at this point, what you're going to see is, here's the schematic of it, and you're going to do a POE, a predict, observe, and explain. Now, the cat is being pulled here. This is a force sensor, so you're going to write in here what you think the force will be. Down here, you can write 10 newtons, easy right there, because you know it's 1 kilogram mass. So the question is, what will it be here? What will it be here? So pause it, predict it, and then in the next slide, we'll take a look and see what the answer is. Okay, so here's the solution. You can see here, it's hard to see, but this is 10 newtons. And over here, it's hard to see again, but this is a 20 Newton scale. So you can see it's at the halfway mark, and it is 10 newtons as well. So there's 10 newtons of force pulling that direction, and there's 10 newtons of force pulling in that direction. Now, your answers may have ranged from 0 to 10, or 5 and 5, 10 and 0, different versions of it. And if you got 10 and 10, give yourself a pat in the back. So what's happening? Well, Newton's second law tells us that the net force on this cat is clearly 0. There's no acceleration. If the acceleration is 0, there's no net force. So that means that the force pulling on this arm and the force pulling on that arm must be the same. They're balanced. So that might have led some of you to and so hopefully, you didn't put 0 and 10 or 10 and 0, because that wouldn't make sense. It would be accelerating. Now, if it's 5 and 5, well, that kind of makes sense. However, because then they're balanced. But imagine that this cat just didn't exist, and that there was just there was a wall here, and you couldn't see, put a little black box around this thing. And you couldn't see inside the black box. You didn't know there was another scale here. You didn't know there was even a cat. You just knew that there was a little rope coming out, a little arm, and it was attached to this thing. Well, you would say, well, if there's 10 newtons pulling down, there must be 10 newtons on this scale. And then you realize, well, if there's 10 newtons pulling on this arm, there must be, and it's not accelerating, there must be 10 newtons pulling back on the arm to keep it from accelerating. So that's your explanation. So that was a predict, an observe, and an explain. Okay, what is Newton's third law? I would write this down. For every force, pause it, for every force there exists an equal and opposite reaction force. Sounds great, but the forces exerted between the two objects, okay, so the forces exerted between the two objects are equal in size and push in opposite directions. Sure. The big part that people often forget is that the forces act on each body independently. So if one body is being pulled, if you have two objects interacting, if you draw the forces on them, the free body diagrams that you draw, the forces are drawn separately on each. So one will have one force and the other one will have the same force but in the opposite direction. So the forces are on each body independently and the force between them is identical. Okay, let's take a look at this. Here's a quick little video where you're going to have two dynamics carts on a somewhat frictionless track. There's a piston loader here where it's going to be cocked, and basically it's going to apply a force to this cart. So they're going to be right together at the very beginning. The guy in the video lights a string that basically sets off the trigger, and what happens is this piston shoots out and it pushes the cart. Now we know that this cart, and you'll see why, that when it pushes the cart, this one experiences the force of this piston. But Newton's third law says that there's an equal and opposite reaction force, which means that even though this piston pushed on this cart pushed back on this cart with the exact same amount of force. Let's watch. Exactly what you thought would happen. Okay, so they reacted and pushed backwards. Now, we know that these two carts must have approximately the same mass because they both accelerated away from each other at about the same rate. And therefore, even though this is the one that did the pushing, this one also pushed back. That's a weird thing, but it's true, and it is Newton's third law of motion. What I'd like you to do now is take out a piece of paper, and you are going to, at this point, you're going to follow this example. So what I've done is I've shown a mass 1 and a mass 2, and you are going to, and there's 100 Newton force applied to each, and we're going to look at what happens to the acceleration of both objects for different mass situations. So get your sheet of paper and copy this example down. And I'll start it again. Okay, so let's consider the situation where we have those two carts, okay? Or any two objects in general. And what we're going to look at first is, let's say that there is a block or a cart of mass 1 and a block or a cart of mass 2. And they're on some kind of surface, frictionless surface, and that's going to be important, frictionless at this point. Okay. Now we've got a frictionless surface and we've got two objects. Now let's assume that the one object pushed off the other object. So in the case before, there was an elastic sort of, or a spring sort of between them, and when they cut the spring or released it, what happened was these two objects pushed apart. Now, in this situation, Newton's third law states that the forces acting on the objects are the same, but in the opposite direction. So it doesn't matter whether the spring was attached to mass 2 or whether the spring was attached to mass 1. So it doesn't matter whether it was mass 1 pushing off mass 2 or mass 2 pushing off mass 1. It doesn't matter whatsoever. The force is equal between the two of them. So what ends up happening is, let's pick a direction to be positive, like so. And let's say that the force acting on this object was in this direction. And so let's say the force acting on it was, let's say, 100 newtons. Okay, that means that the exact same force would be acting on the other object. It would just be in the opposite direction. So the forces that both would feel, so if there was a 100 Newton spring in between the two of them and it let them go and it pushed off, both objects would feel the exact same force, just in the opposite direction. You can imagine that if this was a cart and you were sitting on it and you pushed someone that was on another cart, you would think that you're pushing them, but really you're both pushing each other, because you're pushing off, and then Newton's third law says that that causes reaction force of pushing back on you. And the force is the same between the two of them. And now let's look at the situation for Newton's second law. Well, Newton's second law for the first block is M1A. And for the second one, it's M2A. And we look at that and we say, okay, well, what's the, I'll call it acceleration 1, acceleration 2, just to, give it that distinction. So the forces are the same. So what we're going to do is, what is the acceleration of block 2? So it's the net force divided by mass 1. And the acceleration, the other one is the net force over m2. Now, here's the situation. It's going to be, since F1 is in the opposite direction to the positive direction, it's negative 100 newtons over mass 1. And acceleration 2 is positive 100 newtons over some mass. Now, this is the general case or the general situation. And that seems to make sense. I think everyone's okay with that. Well, what we want to do now is ask ourselves, what happens, if the masses, like what happens with the different types of masses that we can have? Well, let's say that the two objects, like in the previous example, were the same. So let's say they both had a mass of 10 kilograms. Okay, so if they both had a mass of 10 kilograms, 100 divided by 10 is, it'd be negative 10 meters per second per second. So it'd accelerate just for a brief moment in time at that rate. And the other one would accelerate at the same rate of 10 meters per second per second. Okay, well, let's consider a different situation. Let's assume, so another situation. Let's assume that mass 1 is extremely light. So there's still a 100 Newton force acting on it, but it only has a mass of 1 kilogram. And in the other situation, let's say that the mass is 100 kilograms. So this would be like a 1 kilogram block or cart and a 100 kilogram cart. Well, when they push off, what you're going to notice is that the really, really small one, since it has very little inertia, is going to accelerate backwards very, very quickly at 100 meters per second every second. That's incredibly fast, right? That's 10 times the acceleration of gravity backwards. Whereas the other one is going to feel this tiny little acceleration forward. So the one block is going to go shooting back really fast, and the other one's just going to accelerate just a little bit in this direction. Okay? What if this was 1,000 kilograms and this was 0.1 kilograms? This one, it would be like you pushing off a wall, right? The heavier you make the second object and the lighter the other object, the one object just appears to be the one that accelerates, whereas the other one doesn't. You could take the situation of two people sitting on a skateboard. And if one person sitting on a skateboard is extremely light and the other person is extremely heavy, when they push off, the person that's really heavy will accelerate very slowly to the one direction, and the other object will accelerate very slowly backwards. Okay, so you can kind of get that idea of how important it is. But the key understanding here is that the forces are identical between the two objects. They just point in the opposite direction. And we're going to do more examples of this a little bit later. And this will lead us to the question of, like people say, well, if I jump off the earth, if I push off the earth, let's say I push down on the ground with 1,000 newtons of force. I feel the earth pushing back on me with 1,000 newtons of force. But why is it that I jump off the ground? Well, in actual fact, you are pushing off the ground. The earth has to move a little bit. Now, you don't weigh enough to cause any real effect to the earth whatsoever because the earth is so massive. But we'll do that example later on and talk about that neat idea. Okay, so the next thing we're going to look at here is Newton's third law in action. And so this guy here is going to walk us through a really cool demonstration where he pushes off a wall and then he uses projectiles or objects that he throws away from him. And by throwing them away, the force that he pushes on those objects with, they must push back on him. And this is basically the whole premise behind rocket engines, for airplanes, for rockets, for how balloons move when you blow them up and release them. It's all the same sort of thing. You're really just throwing tiny particles backwards from you, and the force that you push them backwards with is what they push you forward with. And this is basically how everything works in terms of travel and motion. for jet engines and those kind of things. So just take a watch of this.
We're here at Purdue University to talk about for every force, there's usually an equal and opposite force pushing the other way. So, for instance, if I push against this wall with my feet, the wall pushes back on me, and I can use that to shoot myself down the hallway. We don't even need a wall to push against. I can push against this medicine ball and throw it that way, and it'll push back at me, and I'll go that way. And this is a lot like how a jet engine works. It actually grabs air and throws it backwards, and that would push an airplane forward. So if I throw this hard enough, I should go backwards. But it's pretty tricky. And I'm traveling backwards at the speed of almost nothing. This doesn't just work with heavy things.
Because
we
there's
can
too much
take
friction.
lots and lots of light things and throw them really fast, and they should push back on me as I push forward on them, and I should still fly backwards. Unfortunately, the question becomes, can I throw them fast enough, or basically push on them hard enough to make myself go backwards? And they're pretty light, so maybe not. But let's give it a try. Here we go. Ow.
In space, this would work.
Ready? Yes! We can now throw even smaller things. We've got a tank of carbon dioxide gas here. And if we let it out, it's speeding out that way. And so it has to be it's being pushed out that way. And so since it's pushed out that way, there has to be a force pushing back on us in order to throw it. And so if I throw basically lots and lots of tiny molecules of carbon dioxide, I can go backwards really fast like a jet engine. I just have to throw them faster. Here we go. 3, 2, 1. Woohoo! And we're gone. The end.
So there you go. So he was able to push, if he were in space and he did those previous ones with the tennis balls, he would actually move in the opposite direction significantly. No, not significantly, but he would move for sure. There's just too much friction between the wheels and things like that. But once he did it with the carbon dioxide, those are tiny little particles. They have so little mass, but they come out so quickly because they're under such high pressure that they come out so fast that there's actually a large force in the opposite direction as well. And that's what propels them. Here's one about flight and Newton's third law, talking about lift, balancing weight, and thrust versus drag, and also talks about how air comes into the fuselage, gets heated up extremely hot, and shot out the back. And when it comes out the back really fast, it pushes forward on the plane, giving it its thrust.
Newton's third law is often thought of as the law of action and reaction. This is a jet engine bay. When the engine's mounted in here, it creates one heck of an action coming right at you. The obvious reaction is it forces the airplane that way. That makes sense. But how does a jet engine work? Just like a balloon that flies away when you let go of it, air comes in here, goes way back into the engine, is heated up, goes faster, comes around the back. It's with a lot of force. That's how a jet works. With all that force, or action, there has to be an opposite reaction. The reaction makes the airplane move forward, just like the rocket sled you saw earlier. But this time the aircraft has wings which provide lift, forcing it into the air. In fact, there are 4 forces, actions and reactions, working every time an airplane flies. The thrust of the engine is one of the forces making the aircraft move forward. But there's an opposing force to thrust, and it's called drag. Drag is the resistance of the atmosphere on the aircraft, like you feel when you stick your hand out the window of the car while you're driving down the freeway. When the drag equals the thrust, then the aircraft is no longer accelerating, but remains at the same speed since the forces are equal. If thrust is added and becomes greater than the drag, the plane will accelerate. As the plane's speed increases, the drag also increases until the thrust and drag are equal again. There are 2 other forces as well. Lift is the force provided by the wings as air passes over the airfoil. The opposing force is, of course, weight. It may seem strange, but lift always equals weight, otherwise the aircraft couldn't stay in the air. As you can see, Newton's laws are really quite simple, but a good understanding of them is essential to the development and flight of aircraft.
It's even more important, we're going to test the airplane. I'm teaming up with some of the best test pilots and engineers at the Dryden Flight Research Center, NASA's home of experimental flight tests. And together, we're going to show you.
Okay. So that was an important thing, talking about how the lift is actually just the air, or sorry, the wings pushing on the air. So the wings push down on the air, the air must push up on the wings, causing lift. As long as the lift matches the weight, you stay in the air at the same altitude. If there's more lift, then you go up. If there's less lift, you go down. And then, of course, thrust forward, which is caused by the engine, throwing air out the back, or particles out the back, and those particles push the plane forward. Once you're going at a constant speed, the thrust force and the drag force are identical. They have to be the same. Otherwise, you're going to be accelerating or slowing, like either forward, speeding up, or slowing down. Here's a simple thing you can do with a balloon. I'm not going to bother showing the whole thing. So you basically have a balloon that's blown up. It has an elastic potential energy, and it's going to compress. So the elasticity of the balloon will cause it to shrink. When it shrinks really quickly, it pushes air out the back. Well, that air getting pushed out the back, that air is pushing forward on the balloon. And then you've got a little frictionless string here, and the balloon should move in the opposite direction to the air coming out.
Today we're going to do
Okay, so of course there has to be cats in there. So yeah, the balloon moves in the opposite direction that it's throwing the air out the back. All right, some other examples. So here's the balloon. So it compresses, it pushes the air down, and the air pushes up on the balloon, causing it to accelerate upwards. Golfing. You don't realize it, but the golf ball and the club feel the exact same force. Yet the golf ball goes, 200 yards, 300 yards, whatever, maybe 100, maybe 5 feet, whatever. So basically, but why is it that the ball moves even though the force on the club is the same? Well, the club is attached to you. You have muscles, and you're heavier, way heavier than the ball, and you're also anchored to the earth. So the earth is extremely heavy. So really, you're attached to the earth somewhat through your cleats and your or your shoes and friction. You have a lot of mass for your body, and you have muscles that can continue the force through. So when you hit the ball, even though the force on the club is identical to the force of the ball is unrestricted motion, and it's the one that accelerates the most. But again, Newton's third law. A ghost pushing on a wall with a skateboard, of course, if you push on the wall pushes back on you. Now the wall's anchored to the foundation's anchored to the earth, so you're trying to push on the earth. Well, basically the earth is much more massive, so you are the one that accelerates, because your force, although it's the same as the force on the wall, causes you to accelerate, and the wall less so. The lift, so as the wings push down on the air pushes up on the wings. If you tilt the wings into the air, you'll get a lot more lift because you're pushing harder on the air, and if you're moving fast enough, and the lift will increase. Put your hand out the window of a car, and when you put your hand out and sort of start to angle it, you'll feel that upward push. Well, really what's happening is you're pushing on the air, but the air's reaction is to push on you with the exact same amount of force, but the opposite direction. Okay, here we have action reaction. So we've got a situation where there is a rocket ship. You heat up the gas really, really hot, shoot it out the back. All these tiny little particles push back on the ship, causing it to accelerate forward. Same forces. Canoeing, well, you don't realize it, but water is really heavy. And when you push back on the water, it causes the same exact forward force on you, but you're attached to the canoe, so you move the canoe forward. The water does move a little bit, although it's much more massive, and it's attached to the earth because it's in a big well of water. And what happens is you push back and it pushes forward for you. Again, equal forces, opposite direction. Cannons. Well, in the old days, people realized that if you put gunpowder in here and a little projectile, you can shoot it out really fast. Thing is, the force on the cannon backwards is exactly the same as the force forward on the cannonball. Now the cannonball has an opening, but you think to yourself, well, why are these cannons so heavy? They're super, 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 super heavy so that you can take a projectile and that when you explode it, it's the projectile that moves, not the cannon. Now cannons have recoil, so this cannon is going to fly backwards, but not as much. This thing's going to come out at hundreds of kilometers an hour and launch really far, whereas this thing will only move back, say, a half a meter. So the heavier this cannon is, it's more important. So the bigger the projectile you want to throw and the more speed you want that projectile to have, the heavier and bigger the cannon has to be in order to absorb the same amount of force, right? And so what they often do is they put springs on these, like really powerful springs, so that when it does, the recoil is less. If you've ever fired, if you've ever gone to a shooting range and tried shooting a shotgun or anything like that, you'll often hear things like recoil. And that's because you're trying to shoot a tiny little projectile out extremely fast, but the gun is heavy, but it's not super heavy. And so it will recoil back into you. So you have to use the weight of your body to absorb that force. Okay. Interesting situations. So now we're going to look at is when you're skydiving and falling towards the Earth's actually falling towards you too, but not very much. And if we all stood at one of the poles and jumped, all 7 billion of us, would the Earth also have to move downward away from us? Okay, a really interesting. Make sure you download your sticky notes for this. Something about skydiving and something about what if everyone jumped on the Earth at once. So one of the things I've put here is that I've drawn. Well, here's the Earth. The mass of the Earth is huge. It's 5.97 approximately times 10 to the 24 kilograms. Here it is written out in full form. It's gigantic. Okay. Now, what a lot of people don't notice about Newton's third law is this. Now, this is way out of scale. Like, imagine the Earth is, the atmosphere is only about that thick. You can't even draw how thick the atmosphere is here because it's so thin. Spaceships and the shuttle and all that kind of stuff, they only fly around this altitude about there. Satellites, spaceships, and that's probably even too high. They're probably not even flying that high off the Earth. So the scale is going to be way off for this. So just recognize scale way, way, way off. All right, let's assume that you have a person and they're going to skydive. Okay, now this person's skydiving from like, way, and somebody, it looks like a dog, I don't know, whatever. And so this person, let's say they have a mass of, it's a big person, 100 kilograms. Okay, now they're falling in this direction due to gravity. Okay, they're going to fall towards the Earth. Well, here's the neat thing. The force of gravity pulling on that person is mass times the acceleration of gravity. So it's 100 times 9.8. So the force of gravity is 980 newtons. Okay, that's the force of gravity pulling this person down. It's 980 newtons. Well, Newton's third law says that if the person is attracted to the Earth with 980 newtons, then the Earth is also attracted to that person with 980 newtons of force. And Newton's third law is correct. It works. It's a universal fact. So that means that this object here is moving downward and accelerating towards the Earth, and the Earth is feeling an upward pull from that person of 980 newtons. But we don't say, oh, the Earth's falling towards the person, we always say, oh, the person's falling towards the Earth. Well, in actual fact, both are attracted to each other. But the reason why it appears that we fall towards the Earth is because of the differences in the mass. So if we look at the person, for instance, okay, and we say, well, what's their acceleration? Okay, and we say the acceleration of the person is the net force acting on the object. We're going to assume no air resistance and all that sort of stuff. So it's a whopping 100 kilograms. And by 100 kilograms, that is not correct. It's 980 newtons divided by 100 kilograms. So the acceleration is 9.8 meters per second, approximately, which is what we knew it would be. Let's check out the Earth. And that's down as positive. Here's the Earth, okay? Well, the Earth is also going to experience an acceleration. proportional to the force and the mass. The force is 980 newtons negative because it's pulling up. But the mass is 5.97 times 10 to the 24 kilograms, or that big, massive number. Well, try to put that in your calculator. So you go 980 divided by 5.97 exponent 24, and you get negative 1.6 times 10 to the negative 22 meters per second per second. This is what, for all intents and purposes, approximately 0 meters per second. It's not 0, but it's almost 0. It's what we would call negligible. So although the Earth does feel the pull of the person falling, it's so small because the Earth's mass is so big, that's what happens. If you had two people in space and they were falling and they had that much force of attraction between them, which they wouldn't because the force of gravity would be so small, the two objects would actually move towards each other simultaneously at the same rate if they had the same mass. Okay, so that leads to another interesting question, which is, what if everybody on the Earth jumped at the same time? And people are always like, well, the Earth would move, wouldn't it? Well, let's look again. Now we got a big person. Again, the scale is ridiculously off. This would be the biggest thing that ever existed, and biggest organism that ever existed. Let's say that you jump. Let's say that the force of the jump, of one person's jump, let's say it's 1,000 newtons of force. It's not a particularly strong jump, but whatever. Let's say they push down on the Earth with 1,000 newtons of force. So if they push down on the Earth with 1,000 newtons of force, the Earth pushes up on them with 1,000 newtons of force. Now, let's see what sort of acceleration, and we'll choose down as positive. What sort of accelerations do each thing experience? But let's make it more interesting. Let's make it all people on the planet. I'm not going to draw all, let's just say it's 7 billion people. I'm not going to draw all 7, I think it's more than that now, but let's not do that. No, I'm not going to draw all 7 billion people on here. So that means that the force that they would apply would be 1,000 newtons per person, assuming everyone's equally strong. So that's times 7 times 10 to the 9. 7 billion times 1,000 is 7 times 10, 9, 10, 11, 12 newtons of force. That's the total combined push-off force of the people. Okay, that means the Earth should experience that. So let's figure out the Earth's acceleration. So everybody jumps, and we've got about 7 times 10 to the 12 newtons of force pushing down. And we'll assume that's times, this number here is what this number pushing down is. Pushing on Earth. So there we go. So the acceleration of the Earth would be the net force divided by the mass. The net force is 7 times 10 to the 12 newtons, approximately, divided by 5.97 times 10 to the 24 kilograms. So we look to our calculator and we punch in 7 to the power of 12 divided by 5.97 to the power of 20, or to the times 10 to the 24, sorry, not to the power. And we end up with 1.2 times 10 to the minus 12 meters per second, approximately 0 meters per second. It would be negligible. As fun as it seems that it would be a really big impact, human beings are quite feeble, quite small, and 7 billion of us don't even take up that much space on the planet if we all crammed ourselves together. Compared to the size of the Earth, we could all fit within about 30 kilometers by 30 kilometers of space if we just crammed everybody together in just square area. If we put ourselves into like a little cube, probably at 10 kilometers by 10 kilometers by 10 kilometers. So anyways, you can realize that it's extremely negligible. And as fun as it is to think about, it doesn't happen. Okay. All right, so this leads us to our consolidation worksheets. There's a video that you're going to watch right after this slide here, so make sure you download this activity. You can just click on the link here if you're in the actual PowerPoint slide or the Google Slides. And you're going to look at a couple of questions where objects are being pushed with a spring that's common between the two of them. And then there's some making connections, sort of consolidation questions that are really important to focus on. So make sure you do these sheets. On the next sheet, it's the last video tutorial within this tutorial. And it explains to you how to do these questions so you can finish off those questions and then answer the consolidation questions that go with it. Okay, so in this last example, we're just going to do a few consolidation questions, and you're going to do these, finish off this sheet on your own. All right, so we're going to consider the situation below where there's two massless boxes, but they contain these two characters. There's a strong spring between the two of them. The spring, when compressed, exerts a force of 12,000 newtons. For each situation, calculate the acceleration of each block, and also if the spring only acts for 0.25 seconds on each block, find the final speed for each block. Include free body diagrams. So we've looked at this problem already before, but this is just some consolidation for it. So we've got Big Bang Beaver over here, who has a mass of 20 kilograms, and Super Turtle has a mass of 12 kilograms. Okay, so the one thing we know is that we'll call this mass 1 for the turtle and mass 2 for the beaver. Okay, so since the force of the spring is 12,000 newtons, we know that Newton's second law says, well, both of these objects will experience the same amount of force, i.e. 12,000 newtons each. But it acts in the opposite direction. Friction is negligible, so we're not going to include it. And so the last part we're going to look at then is to figure out what the accelerations are. Well, without showing all the rearrangements, we just use Newton's second law in each case and rearrange it for acceleration. We're going to pick a direction to be positive. Let's pick this direction to be positive. And we plug in our numbers. So this one is going to be 12,000 newtons in the positive direction over the mass of the turtle, which is 12. And over here we have negative 12,000 newtons, and his mass for the beaver is 20. Okay, so at this point, you're just simply plugging in your numbers, and we knew that the turtle, which has less mass, is going to accelerate more. That was just, we already understand that from Newton's second law and all that stuff. So his acceleration is, the turtle's negative since it's going the opposite way, and the beaver is positive. Okay, so it's negative 1,000 meters per second, which is quite the acceleration. And the other one is 12,000 divided by 20, which is 600, only 600 meters per second in that direction. So we've got the two accelerations for each object here. And now it just says, how fast are they moving if the blocks are acted on by 0.25 seconds? So we just pull out our kinematics equations. And both of them started from rest. So it simply becomes the acceleration times the time like so, and we can find out the final speeds for each object. So it's 1,000 negative times 0.25. That's fast. Negative 250 meters per second. You do not want to be in that situation. If you're in that box, that would be painful. To go from 0 to 250 meters per second in 0.25 seconds is not going to feel good. And the next one, the other box is in the same boat. So we could have probably reduced that spring force a little bit, but that's okay. And there you go. That's all you need to do for these types of problems. It's just a ratio, really. And good luck with the rest of them.